Here, I'll start the recording. So far, we've mentioned that the real numbers are a complete ordered field. Okay, we've mentioned this. We haven't explained all the terms yet. Field is the algebraic axioms. The order part is, well, the order axioms. Okay. We did both of those two axioms in section 2.1, and I think we did that on last Friday, a week ago today. And the thing is, so let me just write that in. This is section 2.1. The thing is, the rational numbers satisfy these two. Okay. So what makes the real numbers special? Well, it's this word complete. Okay, so let's... Yes.
With us seeing the screen right now, it looks really blurry, and it's kind of hard to read what you're writing.
Really?
Yes.
1 second. Does that look better?
Yes, much better.
That is crazy. Okay, let me make it even better then. 1 second. Oh. Wow. Zoom is weird. There we are. How about that? Good?
Perfect.
Oh, I'm sorry. You guys were saying this in chat and I didn't see it. Wow, that's crazy. So that means that the size of that window in my laptop's Zoom is what you get. Okay. Now I know. Always make that window big. Okay. Where were we? Oh, right. So complete. That's what makes the real numbers special. It's what makes the real numbers not the rationals. Okay. So today we're going to have the completeness axioms. And in fact, there's only one. And what it is there's several ways to present this axiom, but we're going to present it as the supremum property. Okay? That is what makes the real numbers not the rationals. Okay? And just before we get into this, just a big picture here. We're presenting all these axioms. We're checking that the real numbers that we have in our heads satisfy these. Again, the one thing we're not doing is we're not proving that the real numbers exist, if that makes any sense. Okay, we're taking that as a for granted that the real numbers actually do exist, and we're writing down properties that they satisfy. And actually, after we write down this next property, we'll be able to say that we won't actually prove this either, but we'll be able to say that any set of numbers that satisfies all these axioms is the same thing as the real numbers. Okay, isomorphic is the fancy math word. Okay, so first of all, let's go back to where we were Wednesday. We were talking about the real number line. So you got 0 somewhere here. You could put the rationals on the real number line, and we all know, I hope, what the problem would be. You'd have 0, you'd have 1, these are rationals. You'd have 2, but then, where would it be? It'd be right around there. You'd have the square root of 2, and that's not a rational number. Okay, so I will state that as a theorem. The square root of 2 is not a fraction. Okay, it's not a fraction of two integers. Okay. We haven't done this proof. The proof is not really relevant to what we're going to learn in this course, so I think we'll just skip it. If you want to see it, it's in section 2.1 of the book. Sort of in the middle of that section for some reason or other. Okay, so what this really means is that the rational numbers have holes. I guess grammatically I should say that Q has holes. If we draw it on the real number line, there are places that there isn't a rational number there. Okay? And then the real numbers do not have holes. And that's what the completeness axiom is. We're going to state it a lot more formally, but that's what we're trying to capture today, is what does it mean to have holes or not have holes, okay? And like I said, instead of just stating the completeness axiom, we're actually going to state an equivalent thing called the supremum property that's just a lot easier to work with, okay? So, we need to get to the definition of a supremum. And to get to that, we need to talk about bounds, upper bounds, lower bounds, and bounded sets. So this is perhaps a bit dry of a definition. I think we're going to be able to get away with, I'm going to leave a gap here, but I'm leaving a gap in the statement of the definition because we might want to go back and put in non-empty there, but we'll see. Okay? So let S be a subset of R. Definition 1, or definition A. S is bounded above if there exists any volunteers for what we should, you understand what bounded above should mean. What should the formal definition be? Anyone brave enough to volunteer?
There exists a real number such that all real numbers in S are less than or equal to that real number.
Mm-hmm. Good. There we go. There exists some real number U such that S is less than or equal to U for all elements S of our set capital S. Okay, so the key is that it really is an upper bound. Okay, and I guess I need to say that in this case. U is an upper bound for S, or of S. Okay. Let me emphasize one more important point. Our upper bound comes from the real numbers, not from the set. Okay, the upper bound does not need to come from the set. We'll get to why that matters here in a minute. Okay. Definition B, the same thing but for bounded below. Okay, so I'm just going to write it this way, bounded below, blah, blah, blah. What would we want? L in R, and L would want to be less than or equal to S for all S in S. And then we'd call L the lower bound of S. Okay. Okay. Third definition is a little bit different. S is bounded if it's both of these. Okay. And then S is unbounded otherwise. Okay. Any questions on those definitions? No? Okay.
So,
yeah, go ahead.
Do we need to add the non-empty subset since we're taking elements and using the less than relation and greater than relation?
Right. Thank you for reminding me. I meant to go back to that. Do we need to add that hypothesis of non-empty right here? Well, is the empty set bounded above? What would this definition say for the empty set? Does there exist a real number that is greater than or equal to all elements of the empty set?
I believe so, because you could just pick any real number.
Indeed. Any real number is greater than or equal to all of the elements of the empty set, because there aren't any elements for which this could fail. Right? That can never fail if S is the empty set. So any real number does it.
How can you use the notion of the relation if there's nothing to compare it to? If we look at the definition, I think we wrote down the definition for that. So we define that the less than that takes two elements of the reals.
Mm-hmm.
So how can we use the relation if we only have one?
That's an interesting question. So the thing is, if S is the empty set, and we go to test this condition that I've highlighted here,
right?
Then we'll say, is this true for all S in S? But S is the empty set, okay? So there isn't anything to test this condition on.
Mm-hmm.
So in a sense, we'll never put anything in there for S in this case, because the empty set doesn't have any elements. Right.
Okay. I guess I'll buy it for now. I'll think about it more.
So we could actually write any statement of the form for all S in the empty set. Something holds. Right.
Is always true.
This is true. Yeah. No matter what you put in there. Yeah.
Okay. So. Yeah. I guess that's just like a little logic rule type thing.
I mean,
to me, it seems like it's like undefined. Like we can't determine whether the statement is true or false.
I wouldn't say it's like a logic thing. I would say if it's a little confusing to you, you should think about it more. Don't think about it as like this is how it is in like propositional calculus or something like that logic. Think about more in the like natural language side. Okay, so for what's the good example, every, if you start a sentence with like every U.S. state that's also a part of Canada satisfies so and so, right? That would be true.
Right.
That would be true, no matter what the condition is, because there's nothing.
Right.
There's nothing that could be a counterexample to it.
Okay.
So the phrase we frequently use here is that this is vacuously true.
Vacuously true. Okay.
Because there's nothing that could be a counterexample.
So it's kind of along the lines of, if it were false, then there's a counterexample, but no counterexample can exist.
Exactly.
Okay, that makes more sense.
Mm-hmm. Good.
Okay.
Cool. So the empty set is bounded above, and it is also bounded below for the same reason. So it's bounded. Okay. So I don't see any reason to add that the subset has to be non-empty into the hypotheses of this definition. So I think we'll just leave it as it is. Okay. Empty set is a bounded set. Where we need the non-empty condition is going to come up here in just a little bit. Okay, let's just do a few examples so we're on the same page. Let's look at, I don't know, the open interval from minus infinity to the square root of 2. Okay. Is it bounded above?
Yeah.
Okay, what's an upper bound?
It's the square root of 2, right?
Square root of 2 is an upper bound, but we could just say 3 is an upper bound too. That definition doesn't say we have to have a good upper bound. It's just an upper bound, right? So by 3 or 4, etc. Or it's also bounded above by the square root of 2. So, cool. Bounded below. No, I mean it goes off to minus infinity. So, nope. So it's not bounded. Okay, so that's important to keep in mind. If you're bounded on one side only, then we call you not bounded. Okay, even though, that's that one, that's just the definition. Okay, to be bounded, you have to be bounded on both sides. Okay. Okay. We already did the empty set. I don't know. Let me point out before we move on. This example, this guy is also bounded above in the rationals. Okay? But if we looked at it in the rationals, then actually square root of 2 would not be an upper bound because it's not a rational number. But we don't have to worry too much about that. We're not going to be talking about upper bounds in the rational numbers at all, just to point out that they don't satisfy the property that we're going to define by the end of the lecture. Okay? So I hope we're all clear on what an upper bound and a lower bound are. We need to go a little bit further. So let S be a, now I do need to say non-empty. Do I? No, I take it back. I still don't need to say non-empty. So S is just another subset of R. Okay. And we're going to define a special upper bound. Okay. The number U in R is a least upper bound. Okay. Or supremum of S. If two things hold, and I hope you can guess what the two things are, just from the name of the term we're defining. It has to be an upper bound, and it has to be the least one of those. Those are the two things we're about to write down. Okay, so it has to satisfy those two things. One, U is an upper bound of S, and 2. What does it mean to be the least one? Well, that means if I took any other upper bound, it would be greater than or equal to this one. Okay? So if V is also an upper bound of S, then U is less than or equal to V. Okay, so we said, not what I wanted to do. We said it's an upper bound, and we said that it's the least of all of those. Okay? Now, let me say that it's easy to keep the definition in mind if you remember it as least upper bound, but we're always going to call it supremum. Okay.
Oh, excuse me, but with this definition, we can't guarantee that U is the smallest upper bound, right?
So this is just a
Even though it
definition.
says least upper bound.
Oh, okay. So this is just a definition. We haven't said that any of these things, that this thing exists, okay? But if this does exist, then if you took any other upper bound, U would be less than or equal to it. So U would have to be the smallest of the upper bounds. Is that okay?
Mm-hmm.
Okay, so it really would have to be the least. But again, we haven't said that these things exist. Okay. Any other questions? Okay. You can guess our next definition. I'm just going to write very briefly. Definition prime. You can also define a greatest lower bound or infimum. And again, it's that infimum term that we're going to use all the time. Okay. I'll leave it as an exercise to you to figure out what the definition of an infimum is, I guess. Or I guess to write it, I'll tell you right now. You can hopefully guess. You have to be a lower bound, and you have to be the greatest lower bound. So if there were any other lower bound, you would be greater than or equal to it. Okay. So what's going on here with with these definitions, let's say we're looking at the real number line. We've got some set S. It's got, say, that interval. It's got some stuff there. So this is our set S. Okay. Then it's got, again, if you've got one upper bound, then you've got infinitely many upper bounds, because anything bigger will still be an upper bound. So it's got, these are all upper bounds of S. And then we've got all these lower bounds over here. Okay, but what we're trying to capture is this notion that somewhere right there is a supremum. Okay, it's the farthest to the left that we can push an upper bound, and somewhere over here is an infimum. Okay, it's the farthest to the right that a lower bound can live. Okay. Any questions?
The generalization of maximum and minimum to sets that are that may be like open on one side or the other.
Yeah, exactly. So let's just make that an observation. We could prove this. Let's call it a proposition. Okay. If S is finite, then S has both a supremum and an infimum. And, well, I want to actually put a definition in here first. I want to give you the notation for supremum and infimum. So let me see if I can manage to do this. I guess we'll do it this way. Erase. There must be a better way to do this, but I'll just make a bigger erase. Okay. So here's your notation. If S has a supremum, then it is denoted sup S or sup parentheses S, one of the two. And if it has an infimum, then that's going to be denoted inf. Or add the parentheses if you like. Okay, so that's the notation for supremum and infimum. And this proposition that we were writing said if S is finite, then S has both a supremum and an infimum. And actually we can say more, the supremum of S is actually equal to its maximum, and its infimum is equal to its minimum.
We need S to be non-empty, right?
Yes, yes. Thank you very much.
Can you clarify why it needs to be empty? Is it maximum or?
Well, it also won't have. It won't satisfy the property if it's empty.
Yeah, let's go all the way back to the supremum and look at the empty set here, okay? What did we say for the empty set? We said every real number is an upper bound, right? So it does not have a supremum. The empty set does not have a supremum because every real number is an upper bound, so there can't be a least upper bound. Okay, so the empty set has no supremum. It has no infimum. It also doesn't have a maximum or a minimum. Okay, so none of these four things that we've got here exist for the empty set. Okay, so we can't write this proposition about the empty set. So we had to add that we're looking at a non-empty finite set. Okay. I think this actually might be, how are we doing on time? Let me skip the proof of this. Maybe we can talk about it. How would you prove this? Oh, fine. Let's prove it. Let's go ahead and prove it. We're going to prove the supremum part. Okay, once we prove that, once we prove the supremum part, we could actually look at the set of all the negatives of elements in S, and then whatever we prove for supremums, we'll extend it in fumums and whatnot. Okay. How do you show that something is a supremum? Okay. You show it satisfies this definition. So we want to show that the maximum element of S is an upper bound. And if there were any other upper bound, then that other upper bound would be at least the maximum element of S. Okay? So let's just work through the definition. Why is the maximum an upper bound? That's the definition of the maximum, right? It's the largest element in the set, so it's greater than or equal to all the others. Okay? Let me write it out, I guess. We know that the maximum... let me be a little bit careful. So we'll start our proof with let S be a non-empty finite set. Okay. How do we even know that non-empty finite sets have maxima and minima? If I ask you to prove that, how would you prove it?
I'd use the ordering properties that we defined previously.
I think you'd have to go back to the ordering axioms, and the proof that pops in my head is I would do it by induction on the number of elements in the set. Okay. And then I would say, suppose S has n plus 1 elements. I would take the first n, take their maximum, compare it to the n plus first element, and, then I get a maximum.
If it's finite, apply the well-ordering principle.
Did the well-ordering principle apply to... Yeah, I'm sorry. Yeah, I guess we did prove the well-ordering principle, or we stated the well-ordering principle. Yeah, okay, good. That would work too. Okay, So by definition, we have that the maximum of S is greater than or equal to little s for all little s in big S. So maximum of S is an upper bound of S. Now, let V be any real number that is an upper bound. So let this be an upper bound of S. Why do we know that V is greater than or equal to the maximum?
V is an upper bound, and so by definition it has to be greater than or equal to every element in the set, and the max is in the set.
Yes, that's the point. The maximum is in the set. The maximum is in the set. V has to be greater than or equal to the maximum. Okay. Those are the two parts of the supremum definition, so we're done. Therefore, the supremum of S, well, exists, I guess, and equals the maximum of S. Okay. So I can't remember who said it, but someone said supremum and infimum are generalizations of maxima and minima to infinite sets, and that's precisely what they are. And when we're talking about finite sets, supremum is maximum and infimum is minimum. And when we go to infinite sets, well, not all infinite sets have maximums and minimums. So let's just consider that for a second. Example, let's go back to our minus infinity to square root of 2. Open interval. Okay. This set has no maximum. Okay. There is no largest element of that set. Okay, because we look at it on the real number line, and we come over here to square root of 2, and we've got an open set there, and we go all the way down. There. Okay. So any element of this set that you pick, there is a bigger one. Right? It's no maximum, but it does have a supremum. So square root of 2 is the supremum of this set. Okay. How do we know that? Well, we have to check the two properties of the definition. First, is the square root of 2 an upper bound on this set? Yeah. Everything in the set is at most the square root of 2. Okay. Could there be a smaller one? Could there be a smaller upper bound? How would we prove that?
You could use a proof by contradiction, assume it exists, and then find a number, say it's X. Find a number, then that would contradict the fact that X is the smallest upper bound.
Okay, let's do it. Could there be a smaller upper bound? Okay, we know the answer will be no, but we're going to try and prove it so that we know how we prove these things. Okay. Suppose we actually don't need to make this a proof by contradiction. we can just say, suppose V is an upper bound on O. Well, I think we do kind of need to make it a proof by contradiction. Suppose V is an upper bound on this set. If V is not the square root of 2, then what would we do? Okay.
Well, then it's contained in the set. So we could take V, we could have square root of 2 minus V divided by 2 plus V. And wouldn't that be between V and square root of 2?
Now you've assumed something that we haven't said, so we need to fix our proof. We're not concerned about V not being the square root of 2. We're actually just only concerned about it being less than the square root of 2. Okay, then what's our picture? We've got V, we've got the square root of 2 on our number line. Anything in between them we happen to know is in our set. Okay, so if we could pick anything in between them, that would be an element of our set, and therefore that would show that V is not an upper bound. Okay? What would be something in between them? It would be V plus half the distance between V and square root of 2. Right? So what we can do, then, because the following element is in our set, V plus square root of 2 minus V over 2. That would be right halfway in between V and the square root of 2. That is in our set. V is not an upper bound. Therefore, square root of 2 is the least upper bound. Okay, which again, that is the same thing as supremum.
Yeah, I still don't understand where the V plus square root of 2 minus V over 2 came from. Like, where exactly did that V plus... Yeah, where did that come from?
It's just this point. I just want a point in between them. This distance right here is the square root of 2 minus V. So that distance here is half of it.
Oh, I see now.
And I'll just add it to V. I'll get something in between.
And I get it now. Thanks.
Yep, no problem. Okay, so what we just did is actually a good blueprint for how you're going to prove that things are supremums. So I want to state this. I guess we'll state it as a lemma because that's how the book does it. Lemma. The number U, which has to be a real number, is the supremum of the, and now let me just think, do I need to add non-empty here? Nope, don't need to add non-empty. Okay, so it's the supremum of the set, well, I guess we'll say subset S of the real numbers, if and only if. Okay, condition 1. S is less than or equal to U for all S in our subset S. That's just being an upper bound. But then part 2 is going to be a rephrasing of the least property. If V is less than U, then there exists an S prime in S with V less than S prime. Okay, and let me just emphasize that's exactly what we did in the proof we just wrote. We found our S prime. It was V plus a little bit more.
Would that also mean that V has to be in the set S if it's ordered and S prime is part of S as well? Or is it not necessarily?
Mm-hmm. Okay, so far we've only looked at intervals, but you should not think that all sets are intervals.
Oh, okay, that's true. Yes.
So yes, sets can have holes all over the place. Okay. So V wouldn't necessarily be in the set. Okay. Any other questions? Okay, again, I guess we've seen this. We already saw this, but it's really important to remember the supremum does not have to be in the set. Okay. Sometimes it is, and sometimes it isn't. Someone asked in chat, Madeline asked, how do we prove the lemma, which we don't have time to prove? How do you prove the lemma without assuming that the real numbers are complete? And what are we doing here? Oh, my iPad went all unresponsive. How do you prove the lemma? Well, the first condition of the lemma is literally just saying, it's just the upper bound condition from earlier. The second condition of the lemma, this is just logically equivalent to the second part of the definition we gave before. Okay? So really this isn't much of a lemma, this is really just a restatement of the definition. Okay? But this I promise you is the version of the definition you actually want to use when you prove that something is a supremum. Okay, so we have 2 minutes left. I really need to, before we end, state the supremum property of the real numbers. Oops. Go away. Okay. There we are. Okay. What do you need to have a supremum? You certainly need to be bounded above. Okay? Because if you don't have an upper bound, you're not going to have a supremum. But there's one more condition. You definitely have to be non-empty, because we talked about how the empty set is bounded above but doesn't have a supremum. So let's take a set that has those. In fact, let's look at every non-empty subset of the real numbers that is bounded above has a supremum. Okay. That is the definition of, that is the supremum property of R. Okay. So now we think about our definition of the real numbers. We said they are a complete, ordered, field, again, we said the field is the algebraic properties. The order is the less than or equal to, that's the order properties. The completeness is another word for this property. And really what this property is saying is that there aren't any holes in that real number line. Okay? So even the interval minus infinity to square root of 2 has a supremum in the real numbers. And that supremum in the real numbers is the square root of 2. Okay? Now just think for a second, in the rational numbers, the rationals don't include square root of 2. So in the rational numbers, this interval does not have a supremum, because if I took any upper bound of this set, that would be a rational number that's greater than or equal to square root of 2. I could find a smaller rational number that's still greater than or equal to the square root of 2. Okay? So this set has no supremum in the rational numbers, but it does have a supremum in the real numbers. Okay. So that's the supremum property. That's the big idea for today. Exercises about this section are going to be like, here's a set, find the supremum, prove that that's really the supremum. There is an infimum property that you could write down. Okay. That follows from the supremum property. If you're interested in the infimum of a set, just take the set of negatives of that set. Look at the supremum of the negatives. Take the negative again. That was the infimum of the set you started with. Okay, so an equivalent property would be to say every non-empty subset of R that is bounded below has an infimum. Okay. Okay, in that case, that's the end of the lecture today. I'll stop our